So it's kind of crazy. These photons going through that barrier, they go through one side or the other side. They go through both at the same time. They go through neither at the same time. Conventional language, how we describe the macroscopic world, is not really sufficient to describe the behavior of things at the subatomic level, of photons, of things that are traveling either really fast or are really light. It turns out that you can do the same experiment with electrons and you get exactly the same kinds of results. You can have them traveling through one at a time, and you look at the pattern on the screen. It looks like they're randomly just hitting. But over time, you start to see that it actually forms a pattern, and that pattern is a diffraction pattern. So these electrons are behaving like particles and like waves, right? And scientists have been uncomfortable with this idea, with this duality, since it was proposed, and have been trying to figure out what are other explanations. And so in current thoughts in physics, I've seen a couple things where people describe particles as moving and creating a wave as they're moving. So there's a wave along with the particle, and so it's the wave that's traveling with it. And it's a wave in what? In space-time. What does that mean? Well, we don't really understand that well, what space-time really is, right? Again, I'm a chemist. That's way beyond me. But what I do know is that quantum mechanics has been an incredibly useful way of describing how electrons behave when they're around nucleuses and atoms and ions and things like that. And it's been a useful way to describe how those atoms and ions interact through the overlap of orbitals, which is how we describe electrons. So what I want to talk about, so we describe the behavior of electrons through mathematical equations. And that's really what orbitals are. It's a mathematical equation that describes how electrons behave. And one of the primary things about quantum mechanics is that it describes the behavior of electrons through a probability of an electron being here or there. Right? You can't say that it's here or that it's there, but there's a certain probability of it being at any point. Right? And until you observe the electron, you don't know where it is, right? It's either everywhere at once or nowhere at once or one place. We just don't know, right? And so it's described as there's a probability of it being in a particular place or not, right? So I want to go through a couple different ways that information is presented, right? And so if you think about, an archer shooting arrows at a target, right? If they're a crappy archer, the arrows are going to be scattered all over the target. Hopefully a few more in the center, fewer out far, maybe, very few actually miss the target. It depends on how good the archer is, right? But before the arrow is actually shot, you don't know exactly where it's going to be if the archer isn't any good. Of course, if it's a great archer, kind of it's all going to be in the center. Pretend it's me. Don't know where it's going to go. Right? So you could, if I shot 1,000 arrows, you can make a mathematical equation that describes what's the likelihood of it hitting the center piece. What's the likelihood of hitting this piece? What's the likelihood of hitting this piece? And you could plot that, right? Apples falling out of a tree, right? You don't know where the next apple is going to fall. It's going to fall somewhere. It's likely to fall closer to the trunk because there are just more apples there, less likely to fall farther away. And so you could get like a picture of that. Well, when we talk about electrons, we can talk about electrons the same way. There's a likelihood of the electron being close to the nucleus, a likelihood that it's going to be farther away. And so for this analogy, distance from the trunk, number of apples in each ring, right? So in the center ring, it's likely that apples are going to fall there, but that ring is pretty small. And so the actual number of apples in that ring is going to be pretty small, right? If the ring was like right around the trunk, there's maybe not going to be any apples there at all. Farther away, kind of in the middle, right, there's a less density of the electron of the apples falling, but there's a bigger area because area goes by r squared, right? So if these rings are spaced exactly equally, the area in each ring actually gets bigger, right? So even though the density is lower, the probability of it being in that area is higher. And then we get out even farther, right? Even though the area gets really big, but there aren't going to be any apples here, right? It has to fall and then roll to get out there. And way out here, there's not going to be any, right? So this kind of a graph, distance from the center, and then probability really of a particle being in that area that far from the center, right? So in textbooks, you'll see plots like this that each of these dots represents a probability of an electron being there, right? You take 1,000 snapshots, and this is what it would look like. A lot of the snapshots, the electron is going to be in close to the nucleus. In some of them, it's going to be farther away. And it's really rarely going to be way out here, right? And so if you just look at the density along an axis, high density close, low density far away, right? So it's on this axis, distance from the nucleus, probability along that line, it's going to be high close in, low farther out. If then you take that slice and turn it into an area by looking at the number inside this circle, inside this circle, inside this circle, and plot that, you get a plot that looks like this, right? Where it starts out close in, there's just not much area, so you get a low probability of the electron being there. Kind of in the middle here, it's kind of the balance between having high density, but also high area. And so you get a maximum probability. The most snapshots have the electron right in that spot. And then farther out, the probability of the electron being out there is much, much smaller. Right? So again, if you take snapshots, you get this probability distribution, you can make a mathematical equation that describes that probability distribution. Well, so in quantum mechanics, they developed the equations for the probability distribution theoretically, right? They worked out what are called boundary conditions, what's the minimum, what's the maximum, and then treated the electrons as waves and kind of saw what mathematics fell out from that, right? And what came out from that are equations, quantum mechanical equations, the Schrödinger equation, that describes the probability of an electron being at any place at any given time when you observe it. Until you observe it, it's this wave that could be anyway, a probability wave, right? But they're just mathematical equations. And so these are the mathematical equations for what's called the radial function of the 1s orbital over here and the 2s orbital over here, right? So they're different orbitals, so they have different mathematical functions, slightly different behaviors, right? So if you look at the 1s orbital, look at the graph, this is that function plotted. High near the nucleus, just drops off, no big deal. That's kind of what we expect. For the 2s orbital, it starts out high near the nucleus, drops off quickly, crosses the axis, becomes negative, and then goes close to 0. So this is kind of interesting. So the actual wave function can either have a positive or negative value. But it turns out that the probability is the square of the wave function, right? You take the wave function and square it, and that gives you the probability. So if we do that, if we take those functions, so these are the wave functions for the first few orbitals, 1s, 2s, 2p, 3s, 3p, 3d, just the radial function. That means if you start in the center and go straight out, what does it look like? So a couple things that we can see. First off, for the 1s orbital, 2 times z over a0, So Z stands for the atomic number. So for hydrogen, it would be 1. For helium, it would be 2. For iron, it'd be 26, right? So that's just a fundamental piece, Z. A0 is the radius of the Bohr radius of the hydrogen atom, right? So this is kind of scaled to the hydrogen atom. And I think it's 52.3 picometers. I don't remember off the top of my head. It's in the textbook, right? It lists what A0 is. And this is actually from the textbook, right? This table, I believe, is in the textbook. And then raised to the 2/3 power times E, right? That's the base of the natural log, raised to the power of negative sigma. And this is just put in there to kind of simplify the graphics, right? The sigma is just Z, again, atomic number, times the distance, radius, so that's really the variable, divided by A0 again, or A0, the radius of Bohr radius, right? So this is actually a pretty simple function. 2 times this fraction raised to a power, times E raised to another fraction, right? Not that complicated. We could use this function, right? I can plug numbers into that function and generate numbers that represent the wave function, right? Again, these equations are the wave functions, the Schrodinger wave functions for these different orbitals. So we see for the 2s, it looks a little more complicated, right? This first part looks pretty similar, but there's a 2 down here. And then the second part, we have 2 minus the sigma times E. So there's a little thing out in front here, and then divide by 2. But again, it's not that complicated, right? It's simple algebra, simple mathematics. And as we go to more higher and higher energy orbitals, 2p, 3s, we just add more pieces to that basic equation. Basic equation, take this Z over A0 with some fractions raised to a power times this other function, exponential function raised to this other kind of piece, something related to this sigma. Right, so like I said, the probability is actually that wave function squared. And so this graph shows the wave function squared. I know that because it's squared. And it also has this r squared term out in front. So that is what you do when you want to calculate the probability of it being in an area, not just going from the center out, right? So the probability along a line, you would not have that r squared term right there. But if you want to look at the area at a certain distance, no matter where you look, you have to add that r squared term there. And so this function gives you the probability of an electron being at a certain distance from the center, right? And so what we see is for the 1s orbital, it has a peak up here. Maximum probability of electron is pretty close, not at 0, but pretty close in. If we look at the 2s orbital, the maximum probability is the peak here, right? It's farther out. And this is for the hydrogen atom. And then for the 3s, maximum probability is even farther out. The other thing we see is that for the 2s orbital, well, there's actually kind of a little bump here that's actually really close to the nucleus. There's a significant probability that the electron is going to be actually closer in than the 1s orbital, right? This peak is closer than that peak is. Right? It's not a lot of electron density, but significant electron density. Well, that's called penetration. You say that the 2s orbital electron cloud penetrates inside the 1s orbital. And that's going to be important later on when we talk about things like, well, shielding. Oops, wasn't ready to do that. The 3s orbital, no, it has 2 of those bumps. One that's close in, even closer in than the 2s, but again, it's way smaller. A second one that's closer than the 2s, and then the main one for the 3s is farther out. Right, so what we can say is that for the hydrogen orbital, the 1s orbital, the electron's going to hang out really close. The 2s orbital is bigger, But that doesn't mean that the electron sometimes isn't closer, and then the 3s orbital is even bigger. Now for hydrogen, there's only one electron, right? And so the electron can either be in the 1s orbital, or in the 2s orbital, or in the 3s orbital. If it's in the 2s orbital, we call that an excited state, right? You have to put in energy to get the electron to be in this 2s orbital. Higher energy farther out. Even more energy to get into the 3s orbital, right? In a given time, if you promote an electron, excite an electron to the 3s, it's going to fall back down into the 1s. Now, if we compare at the same energy level, so this graph shows the R squared for the 3D, 3P, and 3s. So these are at the same quantum level, but different orbital types. You find that, in general, the 3s orbital is bigger than the 3p, bigger than the 3d. Right? The 3s orbital, the electron generally is going to spend more time far away. The 3p, the most likely place where it's going to show up is closer. For the 3d, it's going to be even closer. So s orbitals extend out farther than p orbitals than d orbitals. But the weird thing is, if we look at these, the 3s has 3 bumps. The 3p only has 2 bumps. And the 3d only has 1 bump. Right? So if you look at the 3s, electron's going to spend most of its time out here, but sometimes, a significant amount of time, it's going to spend it there. So it's going to be closer than the 3d. Some of the time, it's going to spend way down here, really close to the nucleus. And it turns out that for the energy of the 3s orbital, this little piece down here dominates the energy. When the electron is down here, it's super stable. And that makes the 3s orbital more stable overall, even though it's a bigger orbital, even though most of the time the electron is spending its time way far away, because the 3s orbital penetrates the 3p and 3d, that electron is at a lower energy than the p and the d orbitals. Oops, I keep hitting the wrong ones. Okay. So that kind of makes sense? I hope so. Okay, so I think we'll take a little break now and do a self-assessment question, and then we'll come back and talk about the last piece.